So I will share my screen. Okay. So I'm sorry that I couldn't type the question. Okay. So I will write it here and we will do the question. Okay. After that, I will send the question. After I type the question, I will send it to you once I type the question. Okay. So we will start with phase modulation. Okay. We will start with phase modulation. So as usual, I will have recap of the theories, what you have learned so far. Okay. Is it necessary? Or may I directly go to the question? Okay, we will have a. Okay. Okay. So first we will see some theories behind the phase modulation. Okay. So first thing is that phase modulation is the nonlinear scheme, no? Nonlinear modulation scheme. Modulation scheme. So nonlinear means several properties are there. Okay. So the first one is this not guarantee the superposition theorem. This is not guaranteed the superposition theorem. Okay, superposition theorem. That is a common property of all nonlinear system. Okay, superposition theorem. And with respect to modulation, another thing is that the transmission bandwidth is very large. Okay, is very large than the twice of the message bandwidth. In linear modulation, this is not happen. Okay, so in linear modulation, always transmission bandwidth is less than twice the message bandwidth. Okay. The other most important property is that in nonlinear modulation, you can increase the SNR, signal to noise ratio, without increasing the transmission power. Okay, without increasing the transmission power. So these are the property of nonlinear systems, nonlinear modulation. Okay. So we will see what happened in phase modulation. Okay. So in phase modulation, already we know that in phase modulation, normally carrier signal phase. Okay, carrier signal phase is changed according to the message signal, no? Message signal. So this is the phase modulation. You already know this. Okay. So you know that typically we are using sinusoidal signal as a carrier frequency. Okay. So typically we are using sinusoidal signal. Okay. Sinusoidal signal as a carrier frequency or carrier signal. Okay. So the reason is that the carrier signal should be RF wave. Okay, the carrier signal should be the RF wave, or it should be an electromagnetic wave. Okay, electromagnetic wave. So all electromagnetic waves are sinusoidal in nature. Okay, so these are normally sine in nature. Okay, so normally we are using sinusoidal signal as a carrier signal. Okay, this is very important one. Okay, so if we consider the sinusoidal signal, so it will look like this, no? So this is the common representation of the sinusoidal signal. So this is a time domain representation, no? This is time domain representation of common sine signal, no? Sinusoidal signal. Okay. So I think already you know that. So uh, if you consider this sinusoidal signal, this is the amplitude, no? This is the amplitude. We know that. Normally it may be a voltage, okay? So measured in volt, okay? So this may be a voltage level, okay? So this is angular frequency, no? We called it angular frequency, angular velocity or angular frequency, okay? And this is time, okay? And this is phase shift, normally measured in radian, okay? This is phase shift. Normally we measured it in a degree or radians. Typically, we measured it in radian. Okay, so I think you know that. Okay, you know that. If we draw the phasor diagram of for this sinusoidal signal, okay, so it will look like this. Okay, so we have, this is our the initial position, and here we have the amplitude. Okay, this is the amplitude. This length of this line represent the amplitude of the signal. Okay, and it is rotating, no? Like this, it is rotating here with the radius of amplitude. Okay, so this so consider participle or point moving along a circle that radius is equal to amplitude. Okay, and this is the angle. Okay, so let's take this theta. Okay, so this is the angle at any time. Okay, so this is for in sinusoidal signal. Normally, this is this participle is moving with the constant velocity. No, it may be omega c. Okay, so this participle is moving with the constant velocity. Okay, like this, and it will create a sine wave. No, so normally we consider a sine wave. The sine wave we considered the projection of this point onto the x-axis. No, so normally this sine wave is creating by the projection. Okay, projection of this this point, okay, on x-axis. Okay, so you can see that when this participle is when this point is moving along this radius, so you can see that the projection is moving here and here, no, like this. Okay, so this the sine wave is creating like that. I think you know already those things. Okay, so what I want to tell you is that if you consider this theta, okay, if you consider this theta, okay, what is this theta? That theta is equal to omega ct, no? If this time point, if we consider this time point is t, so this is equal to omega ct. Okay. So let's I put the phase shift here as 5. Okay. Okay. But you see that at the initial state there is a 5 phase shift. Okay. So we have to include that phase shift also here, no? So if we write the phasor diagram for this signal, okay, if we write the phasor diagram for this signal, so it has initial phase, okay, say this is 5, okay, so it has initial phase like this 5, okay, it has initial phase like this, okay, and after t time, okay, after t time, it will take again another angle, no, from here to here, okay, so it may be omega ct, okay, so omega c is the angular velocity, so now the point is here, okay, so this is the position of the point, okay, and if we consider the angle of the point, so this is the total angle, no, so this is the total angle of the point, let's say it is theta, so you can see that, no? You can see that for this signal, this sinusoidal signal, the total angle theta is equal to omega ct plus 5. Okay. So, any problem with this identity? I think it is clear, no? Okay. So, on the other way, we can see that this omega ct plus theta, this one, this whole terms represent a angle, no? This omega ct plus t plus 5, that represent the angle, no? Okay. Correct? Okay. So, if I tell it further, you know that cos signal is like this. If we plot the cos signal with respect to theta, okay, so it will like this, no? This is the cos wave, okay. So now, if we write it with respect to t, time t, okay, and it also will get the same value here, like this, okay. But for this t, time, for any time instant, there is a corresponding angle, no? This angle, for example, if this point, say the time is t1, so that angle is equal to pi by 2, no? Okay. So every time point, there is a corresponding angle. Okay. Okay. So that is the idea here. Okay. So you can see that at every time point, there is an angle. Okay. So this whole term, it is very clear that this whole terms will represent the angle of the cos function. No? Okay. So what about this theta? If this omega c is constant and this point is moving, no, along this circle, so within time, okay, with respect to time, this theta is changing, no, this theta is changing. So definitely this theta is a function of time, no, this theta is a function of time. Is it correct? Because this theta is changing. Okay, so you can see it here, no? So theta is equal to omega ct plus 5. So you can see that this theta is a function of t. Okay. So can you tell me that this is a linear function or non-linear function? Is this the linear or non-linear? Can you tell? Is this a non-linear? Yeah. Yeah, very good. This is a linear function, no? Because this is in the form of y equal mx plus c, no? Okay. So this is a linear function. You can see. So this theta is changing linearly according to time. Okay. So that is one property of a sinusoidal signal. Now what we are doing in phase modulation? In phase modulation, what we are going to do? Okay, so you know that theta, this is the angle omega ct plus 5. So in phase modulation, what you are doing? Okay. So you know that this is the phase. No, this is the phase of the carrier signal. This is the phase of our sinusoidal signal. No, so that sinusoidal signal we took as a carrier wave. So we can say that this phi is a phase of the carrier signal. Carrier signal phase. So now what we are doing? Now what we are doing? So now we are changing this phi according to our message signal. No? In phase modulation, in PM, we are changing this phi, no? This phase. We are changing this phi phase according to time. No, according to the message signal. No, according to the message signal. So let me tell the message signal is empty. Okay. So this is a message signal empty. So what I am doing? I am changing this phase according to the message signal. So this is the message signal. So typically message signal is also a time function. No? This is also a time function. That means this message signal is varying this amplitude of the message. So normally with MT, we are represent the level, no voltage level or amplitude. Okay, you know that. Okay, so you can see that with the time, this amplitude is changing in this message signal. So that this phi is changing, no? So this phi is changing again according to time. Correct? So we are changing phi according to the message signal, and message is changing according to the time. That means we are changing this phi according to time. Okay. So in phase modulation, what happened? In phase modulation, what happened? This phi, this phase, normally in a carrier signal or sinusoidal signal, this is a constant, no? This is a constant. Okay. This is a constant. But in phase modulation, what happened? This is changing according to the time. Okay. So what happened? This will be a time function. No? This phi will be a function of time. Correct? So we can represent this phi. It is changing with the time. So we can represent it as phi t. Correct? So in phase modulation, this phi become a time function. No? The phase is changing with the time. I hope you get it up to this level. Okay. So I'm sure that most of you have already understood this concept. Okay. But some of you guys may have some confusion. That is why I'm telling it again. Okay. So this phi is a function of time. Okay. So we know that this theta, we previously talked this theta is again, this theta is a function of time, no? Here, okay, we see it here. Okay, so this theta is changing according to the time in normal sinusoidal signal. Okay, even in a normal sinusoidal signal, this theta is changing with the time. Okay, but what happened in phase modulation? Okay, it is again varying, no? It is normally varying with the time, and this phi also varying with the time. Okay, so here this become two time, no? So this become function of a time, function of a function of time. This angle theta will become, initially it is a function of time. It is function of time. Okay, correct? initially this theta is a function of time. Now it is a function of another function, that is phi t, and this phi t is a function of time. Okay, so what happened? This theta t will become, okay, function of a function, and that function is of time. Okay, so it is becoming function of a function of time. Okay, got it? So can you tell me, this one is a linear or non-linear? This theta angle is a non-linear function or linear function of time? Yes, very good. It is linear. Yeah, sorry, it is non-linear function. Very good. Okay, so this is a non-linear function. Okay, so normally we call this as a non-linear. That is why so you can see that it also implies our modulation scheme is non-linear. No? It is non-linear with time. Okay, right. Okay, we will move. So if I draw the phasor diagram of this signal, okay, if I draw the phasor diagram of this signal, so I will write the phasor diagram for normal sinusoidal signal again, omega ct plus theta. Sorry, 5. So it will like this, no? It will like this. So we have initial phi value, it is a constant, and then after t time, okay, after time t, we have, this is AM, AC, okay, we have another angle, okay. So this theta, and so this angle will be omega ct, okay. So this whole angle will become theta plus omega ct, okay. So you know that this theta is a constant, and this point is moving with omega c angular velocity, no? Omega c angular velocity, correct? So this is moving like this with through a circle, no? Like this, okay? So what is the frequency? The moving frequency, angular frequency, that is omega c, okay? And also we can represent it with Fc. So Fc is equal to omega c by 2 phi, okay? So both, okay. So we can say that this has a frequency, angular frequency of omega c, or this point has a normal frequency Fc. The both terms are correct, okay? So if we consider our phase modulation signal, okay? So if we consider our phase modulation signal, it is like this, no? So I will write the phase modulation signal. We know that. So I will write it as like X phase modulated signal is equal to, so we have our carrier signal omega ct plus, okay, plus. So we are changing this file according to the message signal, no? So this phi t will become a function of a message signal. So normally we write it as phi delta mt, no? So this delta t we called as a modulation of index, okay? Or index modulation index, okay? We called it as modulation index, okay? So normally the modulated signal we can represent as AC cos omega ct plus modulation index mt, like this, okay, correct? So if we draw the phase diagram here, okay, if we draw the phase diagram here, you can see that, here, this, okay, so this is the phase, okay, this is the phase. Let's say it is 5t, okay, let's say it is 5t, this one, okay, so I get it as 5t, okay, as a 5t. So if it is 5t, so let's consider some time point, okay, so let's consider at t is equal to t0, okay, so so you can see that our participle, this point will move at t time some phase, no? At t time some phase it will travel according to the time, this 5t, okay? Let's say it is 5t, no? Our angle, okay? Then up to here, it's also traveling with respect to omega c, no? Okay, so so what is the total distance he traveled because of this velocity and because of this phase shift? The both distance he will travel, no? Can you understand? It is just like this. A man is here, okay? Man is here, and he is on some bus or something, okay? And bus is going here with a velocity v, and this man also walk here with velocity v1, okay? So he has this v plus v1, both velocity, no? So if we go into this, so if we find his distance, travel from here to here at some t naught, his the total distance will be v t naught plus v1 t naught, correct? So it is just like this, okay? The only difference is that man has a linear motion, okay? But our point has a circular motion, okay? But you can see that both distance he will travel, no? Both angle. So he will travel this distance with because of this phase shift, and another distance, another angle, correctly speak, it is another angle because of his velocity, omega ct, correct? So the point is here at t naught, okay? Correct? So I hope you got it, okay? And very important thing is, okay? So any problem with this? If you have any problem, you can ask me, okay? So, so you can try to understand it by yourself. If you have any problem, you can ask me by mail or something, okay? Okay. So you can see that. Very important thing is the velocity of this point is omega c. Okay. So velocity of this point is omega c at this time, this t instant. Let's say it is t naught. So it is not changing, no? If we consider another time point here, again the velocity is omega c, no? If you consider this point, again that point velocity is omega c, okay? So we can see that, we can also say that frequency is not changing. Here also the frequency is fc, and here also the frequency is fc, and here any point the frequency is fc, okay, for a normal sinusoidal signal, correct? Okay, so but what here, okay, what is here, what is the velocity here? Okay, so what is the velocity here? So velocity is nothing but omega c plus 5t, no? This is the velocity. Okay, so this is not a linear one. Okay, we can't we don't know how this theta, this phi is changing according to time. So anyway, if we consider any velocity at any point, it will be equal to this one, no? Omega c plus 5t. Okay, so you can see that when this participle is moving from here to here, okay, from here to here, okay, so you can see that the frequency also changing, no? It is not constant, it is changing. This omega c part is constant, but this is changing, no? So you can see that for a phase modulated signal, this frequency is changing here to here and here to here. Okay, so that is the another important thing you should have to understand. Okay, so simply speaking, what happened actually here? So simply speaking, what happened? We are changing the phase of our carrier wave, no? We are changing the phase of our carrier wave. But actually, what is changing? Okay, is it changing the phase? No, no. Actually, this leads, okay, this leads to change the frequency of the carrier. So you can see that indirectly, this is the frequency modulated scheme. No? This is, we are changing the phase, but what happened? It lead to change the frequency of the carrier. Okay, so this is the indirect frequency modulated modulation scheme. Okay, can you understand this? By changing the omega, actually we are changing the frequency of the signal. No? Okay, so by changing this this phase, this part, we are changing the frequency of this whole signal, whole carrier. Okay, but we are normally referred as phase modulation because we first change in the phase modulation, but it results or it leads to change the frequency of the carrier. Okay, so this is also a phase modulation scheme. Okay, so I think using this phasor diagram, you can understand you can see some similar things with PM and FM. In both cases, the frequency is changing. No? In phase modulation and frequency modulation, you can see in both cases, the frequency of the signal is changing. Okay, so another one important point I should recap. Okay, what is that? We can represent our phase modulated signal like this. X phase modulated T is equal to AC cos omega CT plus phi T. Okay, and you know that this phi is changing according to the carrier signal, modulating signal, our message signal. So let's say the message signal is empty. So we can represent this phi T as delta empty. Okay, and this 5 delta empty we normally referred as modulation index. Okay, modulation index. And I want to introduce new parameter for you, but it is not in your lecture note. But I prefer that parameter. Okay, that is we called the phase sensitivity, normally referred with Kp. Okay, phase sensitivity. phase sensitivity. Okay, so this phase sensitivity, we can define it as, okay, we can define it as phi delta is equal to Em. Okay, so this is how the phase sensitivity is defined. Okay, and actually it give the phi delta. Okay, that is modulation index. But with this identity, you can get understand how our message signal amplitude is relate with the modulation index. Okay, so that is why I introduce this this KP parameter, the phase sensitivity, but this is not in your lecture note, but I think it is worth keep remembering. Okay, so so this is another parameter, new parameter. So this is a phase sensitivity. Let's see in when we do the do our example, we will see what is the use of this. Okay, and you know that already know that. Okay, this phi, the modulation index should be within -5 to +5. Okay, this modulation index should be -5 to +5. Actually, this modulation index referred, okay, maximum phase deviation. Okay, so this referred maximum phase deviation, phase difference deviation. Okay. So why it should be within -5 and +5? It is because so this 5t is represent the maximum phase deviation, no? So if the maximum phase deviation is somehow, let's say in this region, okay, so let's say it is 1 to 10 or something, the phase deviation. So you can see that from here to here it is 210, but here to here it is 150, no? So this point can be interpreted with two value. One is plus 210 and other is minus 150. So it will lead phase distortion. Okay, so I think the name is there. I can't pronounce it. Okay, name is there. This is your lecture note. Okay. MB and this one. Okay, this one. Okay, to avoid this ambiguities, no? Okay, so it is called a name, phase ambiguities. I don't know the I think ambiguity. Yeah, maybe. Thank you, guys. I don't know the meaning of that word. Okay. Anyway, that lead to that problem. Okay. Okay. So so our index modulation, sorry, modulation index should be in -5 and +5. Okay, so these are the things we should keep in our mind. Okay, and we have the basic understanding. Okay, so we can do our we can do any problem regarding the phase modulation. Okay, so we have to apply this knowledge by small variation. Okay, then we can analyze or answer some issues relating with the phase modulation. Okay, so so I think it is okay to move to the question now. Okay, so I will move to the question. Okay, so I will again write it here. I'm sorry that I couldn't type it, okay? I don't have a time actually. So before the question, if you need, just take a 5-minute break, okay? Then we will start, okay? If now it is almost 4 o'clock is past, if someone couldn't attend with the lecture, you can leave, no issue, because I will upload the lecture to you. So if you couldn't stay with me, you can leave. Anyway, after 5 minutes, we will again start the session. Okay, we will start our question. Then I can write the question. Okay, I have time to write the question. Okay, so just get a break, a small break.